So we have this linear ODE, and as I said, we're going to use those two basic tricks, standard tricks, in order to try and solve it. The first trick was to recognize a familiar pattern. Well, which pattern do you see in this equation? Well, maybe you're not able to see it yet, but if you look at this equation long and hard enough, you'll notice that the left-hand side almost looks as it's coming from a product rule, right? We have y prime times something plus y times something else, okay? Now remember, if we have something of the form some function I times y, and I take its derivative, by the product rule, that ends up being I times y prime plus I prime times y. This is somewhat similar to what we have on the left-hand side. Again, it takes a little bit of experience to recognize that the pattern we had to begin with is in fact similar to this one. But once we recognize it, we can keep going. Now notice that the pattern that we recognize is not quite complete. We are missing some pieces. So most importantly, in our original equation, we just have y prime, while when we look at this formula coming from the product rule, we have I times y prime. So we have no I in here. So what we have to do is, this is the other half of the trick. Let's pretend actually that we do have a function I in mind, okay? We're going to find out what that function is. But let's pretend there is some function I that is going to do the trick, okay? So what we're going to do is we're going to multiply both sides of the original equation by this ghost function I. Okay, so what are we going to end up with? Well, the original equation becomes y prime times I, or I times y prime, plus I times f times y equals I times g. Remember, I have to multiply both sides. All right, well, it looks like we got it, but not quite, do we? The left-hand side has become closer to the derivative of a product. In fact, it is the derivative of a product as long as the two pieces will match. So in other words, as long as the function I'm looking for is such that its derivative is equal to the original function times the function f of x, which I have in my original equation as the coefficient of y. Okay? So now I'm saying, all right, if I can find a function I that does this, that has this property, then I may be able to read the left-hand side as coming from a product rule, and who knows, maybe I'll be able to integrate. Okay? But notice that this equation that I just wrote down is an ODE which is actually separable. Remember, the left-hand side is I prime, which I can write as di by dx equal to if, and I can separate the two pieces, right? So I can write the left-hand side as di divided by I, and the right-hand side is f, which remember is a function of x, times dx. So that means that I can solve this last differential equation, and so I can come up with a function I which has the properties that I need. Remember, we started by saying, well, let's pretend there is one. Well, now we know how to find it. So let's keep going and see how we can find this function I. Alright, so we've started from our linear ODE, which is the one you see on the top left. We've multiplied by this yet unknown function I. We end up with the function on the top right side. And what we know about this function I is that it has to satisfy this particular differential equation, which we have already separated. Alright, let's proceed to integrate. On the left-hand side, we have the integral di over I, and we know that it integrates as the logarithm of the absolute value of I. And the right-hand side, well, we're not quite sure what it is because it depends on f, but hopefully we'll be able to find what that integral on the right-hand side is. Okay. Now we're dealing with the usual problem of finding an explicit solution for this separable ODE. We've got an implicit one, but we need an explicit one. But we have a couple of simplifying situations here. Remember that all we're looking for is one function that does the trick. Okay, so we're not looking for a whole family of functions or anything like that. All we want is one function that will help us in our quest. So what we're going to do in order to make our next steps easier is, first of all, we're going to assume that the function we're looking for is actually positive, so we don't have to worry about those absolute values. And also, since all we're looking is one function, is we're going to assume that the constant of integration c is simply going to be 0. Just makes our life easier. So if we do that, then we end up with the ln of just I, not absolute value, is going to be equal to the integral of f, which of course we still don't know what to do because it depends on what f is. But now we can take exponentials on both sides, and so we end up with I of x being equal to e to the power of the integral of our function f of x in the x. So that is the function that we're going to need in order to be able to completely solve the linear equation that we started with. So this particular function, this ghost function that we've been after since the beginning of this class, is actually what we're going to call the integrating factor. That's why I called it I of x, and of course it's called the integrating factor because it will allow us to integrate enough to solve the linear differential equation. So we're not done yet, so let's see how we complete all of this. So let's put all of this together. So what we said is, all right, we start from a linear differential equation. We pretend that we're multiplying left hand side, right hand side. Well, we don't pretend we're multiplying. We multiply the left and right hand side by this function I, which originally we didn't know what it was supposed to be. Now we found out it's simply the exponential of the integral of the coefficient of y. Okay? And the reason we do that is because now the left hand side is the derivative of a product. All right. So what we're going to be doing is we're going to write the left hand side as the derivative of a product. Remember, the left hand side of our equation, so this side here, this whole expression, that's pretty much the derivative of I times y, right? It's I times the derivative of y plus the derivative of I, which we found out is in fact I times f times y, and then the right hand side is ig. All right, now if we take the integral on both sides, remember the left hand side we already have the derivative of something, so the integral, the indefinite integral, will be simply the original function iy, and on the right hand side we'll have the integral of I times g. And again, what that integral is depends on what g is and what I turns out to be, and so on, and we're going to have to hope that that integral is computable. If it is, then all we have to do is just write down the solution as y equals 1 over I of x, which is our integrating factor, times the integral of I of x times g of x. And we have solved our equation. Okay? Couple of catches though. Okay? The whole technique is very good. In fact, we come up, notice, with a formula which can give us the solution of our differential equation in what looks like just one step. But it's not really, because in order to write that formula on the right hand side, we still have to compute I of x, which involves one integral, and then we have to compute that remaining integral on the right side. So what that means is that we need to still compute two integrals in order to put that formula together. However, assuming that we can do that, and of course in all the examples that you will be asked to solve, this will be possible. Then we can actually solve the equation. By the way, this looks like a very complicated method, but it's in fact one of the first methods that was developed in order to solve differential equations. In fact, it is due to Leibniz himself.